Thank you. Well, I took the liberty of changing the title slightly and including magnesium. And some of you may know Everett Schock. He once said, never read your own abstract. But I did, and I noticed magnesium is in there, so I think I have the right to talk about it. Actually, I will focus on magnesium. The major reason for that is I wrote this paper with Herrick Berszewski recently. It is still online first in OLAB. And when we did it, I asked Herrick, can't we include magnesium, divalent magnesium as well? And Herrick, who's a biochemist, said, no, for a biochemist it's trivial. Any biochemist would know that you need magnesium, divalent magnesium, to carry out prebiotic reactions. And I noted yesterday that even Jerry Joyce uses 25 millimolar magnesium chloride in his systems, which is half of the concentration of magnesium in the modern ocean. So it's quite a lot. Well, Herrick worked a lot. He was in this society earlier on pyrophosphate and pyrophosphatase, PPases. And he was struck by an earlier article by myself and my group about the chemistry of the Mariana subduction zone, which is a sediment-starved subduction zone in the Western Pacific between the Philippines plate and the Pacific plate, the Mariana Trench. These are you could call them cold seeps. They're not hydrothermal systems. It's a dehydrated subducting slabs that produce mud volcanoes out of brucite, magnesium hydroxide, and calcite, both aragonite and calcite, actually. So this is a picture, a cartoon of modern subduction. You would see the spreading ridge, where you find what most people call hot vents, hydrothermal vents, but what we would prefer to call hydrothermal systems. New ocean floor produced by basalts at high temperature, of course, but produces a low pH. And then you have the vast area here of ocean floor spreading, takes millions of years, and you would have here what Barbara Sherwood-Lala talked about yesterday, water-rock interaction, which is a major process in the ocean floor, actually. And then you have the subduction zone, where you again have dehydration, subduction, and decarbonation, and whatever. And you go here with fluids from a low pH through ultramafic rocks in the overriding plate at very high pH, and then again into low pH. So it's a complicated system. But with regard to early plate tectonics, it looked probably fairly similar to this. The difference being perhaps that the basalts produced here were less silica containing, more magnesium rich, and then maybe a different scale of plate tectonics. So, but we don't know too much about that. But Minik mentioned that plate tectonics was probably around at 4 billion years ago. So these are profiles from the Mariana mud volcanoes. This is the South Chamorro Seamount. These are actually they're carbonate chimneys, and this is profiles of the pore water coming out from these, well, not too deep down. It's in meter below seafloor. But what you can notice here is that you have a pH rising from seawater 8 up to 12.6. Which is kind of a very different system from what we have been thinking of with regard to pH normally for the origin of life. What struck Herrick more than myself was the concentration of sodium going up from 450 millimole per kilogram up to 600 something down in the sediment pile. And what I've been interested in before is the boron concentration. You know, the papers by Benner and Prieur about boron stabilizing pentosis going up from 0.4 to 4 millimole per kilogram in these waters. Then this may indicate something, of course. So we produced this scheme in the article that probably the first living systems were pyrophosphate driven with PPases, with a sodium pump and then going over to a proton pump and ATP as the energy carrier. And actually what interested me here in this context is that the PPases require presence of magnesium, divalent magnesium for them to function through the membranes. And you also, pyrophosphate, forming pyrophosphate, you do it normally in systems containing magnesium. Actually, you can do it fairly easily at geologically moderate temperatures from like 150 to 180 degrees Celsius. Well, Barbara also talked of serpentinization yesterday, and this is one of the varieties that you can illustrate it with. You start with olivine, which is a solid solution between forsterite and phyllite, iron magnesium silicates, and you make serpentine. But what's geochemically interesting is primarily that you form hydrogen, elemental hydrogen, by reducing iron, oxidizing iron 2 in the olivine and to magnetite, and then reducing water to hydrogen. But you also get an excess, if you're below 300 degrees Celsius, something, you get an excess of magnesium, and normally you have it in the form of brucite, which could also then incorporate iron, ferrous hydroxide. But so there is not a lack of magnesium in the system. This is a solid compound, of course, but when you decrease the temperature, it tends to dissolve, so you would have plenty of dissolved magnesium around. Forsterite, the magnesium hydroxide is olivine is a nesosilicate. You have single silica tetrahedra together which are coordinated by magnesium, and magnesium is strictly octahedral. It always likes to coordinate 6 oxygens, regardless of the form of oxygen. It could be oxygen ions, or it could be water, it could be hydroxyls or whatever, but it likes to coordinate. I'm not aware of any other atom coordinated by magnesium. So you have the octahedra here, and this is forsterite. And here you have the pure brucite. In brucite you have just the magnesium, divalent magnesium surrounded by oxygens, and they sit together. Or you can substitute some of it by other cations like iron and aluminum. So, well, if you have strict aluminum, you're into gibbsite, the dioctahedral structure. And in the origin of life context, you often use montmorillonite as a catalyst for prebiotic reaction. That's still, you have the magnesium octahedra here. This is saponite, then if you have magnesium. Otherwise, with aluminum, you would have montmorillonite. But it's there all the time. So this, actually, why I got interested in magnesium so recently is because I attended an NII Executive Council meeting in Atlanta, Georgia Tech, in January as a guest, trying to be for us to be an associate member of the NII. And there were presentations by Lauren Williams' group at Georgia Tech. And this is a picture of the inner coordination shell of magnesium. So you have just 4 of the magnesium in one plane, and then oxygen in one plane, and then you have oxygens, of course, on top and bottom. And what magnesium can do that no other cation can do is to incorporate oxygens of other molecules, or 2 different, for instance, 2 different phosphate molecules into its inner coordination shell. So it actually is the reason for in RNA, one of the reasons in the RNA for bidentate clamps. So you connect 2 different phosphate molecules for the folding of it. So actually this is the reason why nucleotides in general are stabilized. You have the magnesium preferably stabilizing between the beta and gamma phosphate groups, and you make a 6-member rings out of magnesium, oxygen, phosphorus, oxygen. And this is actually also the reason why you can make polyphosphates easily in the presence of magnesium. It stabilizes the molecules. Actually, it's necessary for you to have magnesium present when you make the ribosomes, the ribose enzymes. And also, like for instance, in prebiotic chemistry, you often use trimetaphosphate for phosphorylation, but to open that, to have a straight triphosphate chain, you need the presence of a magnesium, divalent magnesium for stabilization. Well, this is from a paper by Lauren Williams groups as well. It's from a paper 2009 called Peeling the Onion. This is the large subunit of ribosomes, starting with the PT origin in the center, the peptidyl transfer, and going outwards from presumably older to newer parts of the ribosomes. And you remember Ada Jonath talked about the ribosomes and their antiquity 2 days ago. So what's special about that is that, well, one thing that's special is that when you go from the PT center too close to the surface, you go from very high density of magnesium, I can't even see it, to low density, and magnesium is towards the surface replaced by in the chemical processes leading to the origin of evolution of life. But exactly how that happened, I do not know. So thank you.